So today I'm going to show you a one-size-fits-all method for difference equations. So I'm going to show you one method that you can use to solve any type of difference equation, no matter what comes up. This assumes, by the way, that you've already done the chapter and you're looking for a revision or a faster way to do it. So I will be assuming that you know some things. I might make videos about difference equations from scratch in the future. But yeah, this assumes that you can already solve difference equations. In particular, you need to be able to solve a second order inhomogeneous difference equation using the method that's usually taught on the applied maths course, which I will briefly go through now just to show you how to do it. But basically, we're going to use this exact same method for all types of difference equations, all four types. Now, if you are familiar with this method, I'd suggest that you try it yourself. Try to do the method on different types of difference equations, the first order ones and the second order ones, homogeneous and inhomogeneous. Try doing it yourself first and see how you get on, but if you're not sure, I'm going to do one example of each in this video, starting with a second order inhomogeneous difference equation, since this is probably where you learned this method in the applied maths book. So it's second order because we have three Tn terms, and it's inhomogeneous because we have an extra function of n on the right hand side, though it doesn't really matter what side it's on, but we have an extra function of n. We don't just have Tn terms. And then we're given initial conditions as always. So when you're solving one of these equations, and if you're going to use the method that I'm showing in this video for all difference equations, you're always going to write down complementary and particular. So these are the two different types, two different steps, I suppose, in doing a difference equation. Now, we're going to start off with the particular solution, although it doesn't really matter which one you start with, but I'm just going to start with particular because I find it tends to be a bit more straightforward. So the particular solution is the part that's particular to this difference equation, which means we're going to be ignoring all the Tn terms. So we're going to be ignoring all of these, and we're just going to be focusing on the function part, I suppose. So our function part here is 5n minus 6. And what you want to do with this for our particular solution, which I write as Tn with a p up here, that's not to the power of p, that's just a little way of saying it's the particular solution, is we're going to take this function and we're going to generalize it. So this is a linear function, so we're going to write down a very general linear function. So I'm just going to write an plus b as a way of writing a linear function. We have an n term and we have a constant. Just to show how it would work for other types of functions. So for this example, we have 5n minus 6, so our particular solution is a linear. If we had just a constant, so for example, if I just had minus 6 on the right hand side and the rest is Tn's, well, we just have a constant, which means our particular solution is just a constant. If our particular part is just an n, our particular solution is still going to be linear. Don't just write an because it's still a linear equation, a linear function, sorry, and we have to treat it as general as possible. If we have a quadratic, we write down a general quadratic. Even if we just have n squared, we write down the whole quadratic. If we have a exponential, so something to the power of n, we write it as some constant times that same number to the power of n. And if we have a constant times a number to the power of n, it's a different constant that we don't know times the same base to the power of n. But we'll see get more examples of those as we go. Again, this isn't a tutorial on how to do this method, it's just how to use it for all different equations. Now to find out what a and b are, we know that this equation is true, so we need to be able to sub this into this equation to figure out what a and b are. Now we can replace the Tn here with this Tn, but the thing is we don't have Tn plus 1 or Tn plus 2. So in order to fix that, what we can do is we can sub in n plus 1 and n plus 2. So to figure out what Tn plus 1 is for our particular solution, we'll have a times n plus 1 plus b, which is equal to an plus a plus b. And then to get what Tn plus 2 is in our particular solution, we can have a times n, that's very bad, a, whoops. We can have a times n plus 2 plus b, which is the same as an plus 2a plus b. Now that we have Tn plus 1 and Tn plus 2, we can now sub into this. So I'm just going to write it down here again, just for convenience. Oops, I didn't mean to put it there. I'm going to write it down there. I'm going to move this over to give myself a bit more space. All right. So we're going to sub in now to find out what a and b are. So Tn plus 2, I'm going to replace that with this. So instead of writing Tn plus 2, I'm going to write an plus 2a plus b minus 8. Instead of Tn plus 1, I'm going to write an plus a plus b here. An plus a plus b plus 12. And then instead of Tn, I'm going to write an plus b. I'm very bad at writing the a's. An plus b, which is equal to 5n minus 6. Now we need to simplify this. So we have an minus 8an plus 12an. That's going to be 5an And then we'll have 2a minus 8a is going to be minus 6a. And then we'll have b minus 8b plus 12b is going to be plus 5b equals 5n minus 6. How can we figure out what a and b are from this? Well, in order to do that, I'm going to do a quick little aside. It's not related to this. It's just a little example to get you kind of familiar with this. If I were to say, for example, that ax squared plus bx plus c is equal to 3x squared plus 9x minus 2. And I said, what's a, b, and c? Well, obviously, a is equal to 3, b is equal to 9, and c is equal to minus 2. How did you do that? Well, you compared the coefficients on both sides of the equation. So we can do the exact same thing here. So we want to get all the stuff with a's and b's to one side and all the stuff that doesn't have them to the other side, but they already are. And we can compare the coefficients. So the numbers in front of the n's have to be the same, as over here the numbers in front of the x's had to be the same. The b had to be the same as the 9. So the numbers in front of the n's have to be the same. So 5a has to be equal to 5, which means that a is equal to 1. And then the constants also have to be the same. So this constant has to be the same as this constant, which means that minus 6a plus 5b has to be equal to minus 6. Since a is 1, we know that minus 6 times 1 plus 5b is equal to minus 6. Solve this equation and you'll get that b is equal to 0. So a is 1 and b is 0, which means our particular solution is an plus b, but we found out what a and b are, so it's going to be 1 times n plus 0, which is just equal to n. So our particular solution is n, and we're done with the particular solution now. So that's the first step of solving the difference equation. The second step is the complementary solution. So the complementary one is the opposite of the particular one. So for the particular one, we ignored anything that was a Tn. For the complementary solution, we're going to ignore everything that isn't a Tn. So I'm going to ignore this part that we just worked on. And we're going to pretend that it doesn't exist, and we're going to solve it as if that didn't exist. So we're just going to take the part with the Tn's and pretend that the part that isn't Tn's doesn't exist. We're just going to say 0. And now we solve this as if it was a homogeneous difference equation, which is covered in the book. So we write the characteristic equation, which is x squared minus 8x plus 12 equals 0. Solve this, we'll get that x, and then we'll have minus 6 times x minus 2 equals 0, which means that x equals 6 or x equals 2. So our complementary solution then is going to be some constant, which I'll call alpha, alpha times 6 to the power of n plus beta times 2 to the power of n. And that's our complementary solution. Now we can't figure out what alpha and beta are because we can't just sub this in back in to here. You'll find it runs into problems if you do. You can try it out if you really want to, and it takes forever as well. That's the other problem because you're dealing with no n's in the exponents. So what we do instead is we're going to get our final solution first. So, and then once we have our final solution, we can figure out alpha and beta. So the final solution is always going to be, you take the complementary solution and you add it to the particular solution. So our final solution is going to be the complementary solution, which is this, plus our particular solution, which is, as we see over here, our particular solution is just n. So we're just going to do plus n. Now this is our final solution. And we know that in our equation, t0 is 1 and t1 is 4. So that means if t0 is equal to 1, that's the same as replacing this n with a 0, replacing this n with a 0, and replacing this n with a 0 and this one. So we get alpha times 6 to the power of 0 plus beta times 2 to the power of 0 plus 0, or in other words, 1 is equal to alpha plus beta. That's our first equation for solving alpha and beta. We also know that t1 is 4, which is given in the question. And that's going to be equal to, replace all the n's here with a 1, because it's the first term. We'll have 6 alpha plus 2 beta plus 1, or in other words, 3 is equal to 6 alpha plus 2 beta. All right? And now we can solve these equations simultaneously. I'm going to use elimination just because it works out quite nicely here. So I'm going to multiply this equation by 2. So we'll have 2 equals 2 alpha plus 2 beta. Subtract. Then we'll get 1 equals 4 alpha, and the betas will cancel, which means that alpha is equal to a quarter. Now, since alpha plus beta is equal to 1, a quarter plus what is equal to 1? Well, the answer is that beta is equal to 3/4. So now we know what alpha and beta are. Now we know what our final solution is, because we know that Tn is equal to this. This is our solution. but we know what alpha and beta are now. That means that Tn, the nth term, is given by 1/4 times 6 to the power of n plus 3/4 times 2 to the power of n plus n. And that is our final solution for the difference equation. Now you can check this. You can use the difference equation up here to figure out different terms. So for example, we know that when we sub in 0, we should get 1. You can check that here. When we sub in 1, you should get 4. Check that here. If you sub in here to figure out what T2 will be, and then you can check here as well if you want. You don't have to do that, but it's good to check, of course, always. So yeah, that's the method that we're going to be using for the 3 other types of difference equations. Now that you've seen it, I'd recommend you try using the same method for other types, and if you're not able to, you can come back and look at one of the examples here. So next, I'm going to look at an example of a second order homogeneous one. So the difference between this and the last one is that we don't have this little bit at the end. We don't have the 5n minus 6. This time we only have Tn terms, which makes our lives a bit easier. So we do the same as always, complementary and particular. Now, one thing that also helps is if you get all the Tn's to one side, and then if you have the other stuff as well, the function part, put that onto a different side as well. You don't have to, but it just makes things a little easier. So I'm just going to write the Tn plus 1 minus 14Tn plus 49Tn minus 1. I'm going to write that that's equal to 0. And it just makes it a bit easier. So for our particular solution, we see what's not a Tn. So we're going to ignore all the, oops, didn't need to make that red. We're going to ignore all the things that are Tn terms. We see that as just 0, which means there's no particular solution. Or in other words, our particular solution, Tn particular, is just equal to 0 because it's 0 there. So we don't have to actually worry about a particular solution, and we can just move on to the complementary one. So we can just solve the characteristic equation here. We'll have x squared minus 14x plus 49 equals 0. By the way, it doesn't matter if this is n plus 1, n, and n minus 1, whereas up here it was n plus 2, n plus 1, and n. You use the same method regardless. It's the only difference it's going to make is if you have a particular solution, the numbers you sub in here are going to be a little different. So we'll just solve this characteristic equation. We'll get that x minus 7 times x minus 7 is equal to 0, which means that x is equal to 7, or x is equal to 7. So we have a double root here. So if you remember from the book, when we're writing a complementary solution, we'll have some number, I'm just going to call it alpha, times 7 to the n, plus beta times 7 to the n. But the problem with this is just an exponential. So to fix it, one of the theorems in the chapter is that if you have repeated roots, one of the terms gets an extra n in it. And then our final solution is always the sum of the complementary and the particular. But in this case, our particular is equal to 0. So the final solution is just our complementary solution. So our final solution is just this. And then we can find out what alpha and beta are using this information here. So we're told that T0 is equal to minus 1. So T0 is equal to minus 1, which is equal to, sub in 0 for all the n's. So we'll have alpha times 7 to the power of 0 plus beta times 0 times 7 to the power of 0. This term is going to be gone because it's multiplied by 0. So all we get is that alpha minus 1 is equal to alpha. So we didn't even have to do simultaneous equations there. And then we're also told that T1 is equal to 14. So that T1 is equal to 14. Replace all those n's with a 1. We'll have is equal to alpha. Now alpha's, I'll just write alpha actually. Alpha times 7 to the power of 1 plus beta times 1 times 7 to the power of 1. So 14 equals, now alpha is minus 1, we know that, so I'm just going to replace it with minus 1 times 7 is minus 7 plus, and we'll have 7 beta. So we'll have 21 is equal to 7 beta, which means that beta is equal to 3, which means our final solution, which we can take from here, Tn, is going to be equal to alpha, which is minus 1. So we'll have minus 7 to the power of n plus, and then beta is 3. So we'll have 3n times 7 to the power of n. And that's our solution for this difference equation. Again, you can check by subbing in the values here and checking if they match up with the values you get out here. So now we're going to look at an example of a first order inhomogeneous one. So same as always, we're going to do complementary and particular. So we're going to start off with the particular. Well, we see, again, it's helpful if we get the un's onto one side and then the other stuff onto the other side. Again, you don't have to do that. But if we do, we'll see it's a bit easier. So we'll have that un minus a third un minus 1 is equal to 2. If we ignore all the un terms, which is what we do for our complementary, or our particular solution, sorry, we see that it's just 2. It's just a constant. That means that our particular solution is also just going to be some constant, which I'm going to call a. Now we want to sub this back into our original equation to figure out what this constant is. We want to sub this back into here. Sorry, I wrote TNP, but here we're working with UNs. It's the same thing. It's just a little labeling difference. I can sub in the UN with this, but I can't sub in the UN minus 1. So what I'm going to do is I'm going to find out what UN minus 1 for our particular solution is. But when you change it to n minus 1, you can see there's no n to change here, so it just stays as a. So then we can sub this into our original difference equation. Okay, so we'll have a, just subbing in, so replace un with a for our particular, minus a third times a equals 2. This means that 2/3 a is equal to 2, which means that a is equal to 3. So that was quite easy. So our particular solution is just equal to 3. Now let's do our complementary solution. So remember, when we're doing the complementary one, we ignore everything that's not a un. So we ignore this. So we're going to have that un minus a third un minus 1 is equal to 0. And we're going to get the characteristic equation as we did up there. So we're going to take the lowest kind of term of the n to be a constant, so which is this one. And then we're going to take the next one up as an x, same as here. We took the lowest one as a constant, the next one up as an x, and the last one as an x squared. Now since there's only 2, we're going to take the lowest one as a constant, and the next one as an x, and then there's none for an x squared. So what we'll have is just x minus a third is equal to 0, which means that x is just equal to a third, and that's our root. So our complementary solution is just equal to, we'll have some constant, which we'll call a, or alpha, sorry, times 1 over 3 to the power of n. And then if we had another root, we do plus beta times whatever, but we only have 1 here, so that's our complementary solution. Then our final solution, Tn, is always going to be the complementary plus the particular, which means that Tn is going to be alpha times a third to the power of n, and then our particular solution is just 3, so we'll do plus 3. Now to find out what alpha is, we're given the initial information that u0 is equal to 32. I've been writing Tn this whole time because I'm not thinking straight, but it's technically should have been un, but it's just a labeling difference. We can say that u0 is equal to 32, u0 is equal to 32, which is equal to alpha times a third to the 0 plus 3, which means that alpha is equal to 32 minus 3, it'll be equal to 29. So that, and then our final solution is that un is equal to alpha, which is 29, times a third to the power of n plus 3. And that is our solution. So then our final type is a first order homogeneous, which looks like this. Again, you don't have to remember the types, I'm just going through them all. So again, we're going to have complementary and particular. I'm going to take all my Tn terms onto one side, as I did. I don't know why I keep mixing up the T's and the U's. It doesn't make a difference though. I should have just read T0. So then we can just move them all to one side. Tn plus 1 minus 2Tn is equal to 0. You can see when we ignore all the Tn terms, oops. When we ignore all the Tn terms, you can see our particular solution, there is none. So that's what homogeneous technically means. There's no particular solution. So our particular solution, Tn particular, is just equal to 0. Now let's look at our complementary one. So we're going to get the characteristic equation. So we're going to take the lowest Tn as a constant, then the next one up as an x. So we'll have x minus 2 equals 0, which means that our root is x equals 2. So our complementary solution will be equal to some constant times 2 to the power of n. Our final solution then is just, our final solution, not our complementary, is going to be our complementary solution plus our particular solution, of which there is none. So that means that our final solution is just alpha times 2 to the power of n. What's alpha? Well, we know that T0 is equal to 5, which is equal to replacing that n with a 0. We get alpha times 2 to the 0, which means that alpha is equal to 5. That means our final solution, Tn, is equal to 5 times 2 to the power of n. And you could technically solve that using normal maths. It's a geometric sequence. If you divide by Tn, you see that Tn plus 1 over Tn is equal to 2, and you can actually solve the common ratios too, and you can solve it that way as well, but this is just using the same method for all 4 types, and that's it. So you can let me know in the comments if you have any questions, and hopefully that was helpful.